Well, welcome everyone to the TIEEP Spring Energy Forum. I'm Alan Rossiter with UH Energy, and I'm your host for this event. TIEEP is funded by the State Energy Conservation Office and operated out of the University of Houston. The theme for our session today is decarbonizing the process industries. Of course, energy efficiency is a very important tool for decarbonization. However,
yes, the IV thing is beeping at us.
I'm afraid we may have to mute people if we have too much interference here. Of course, energy efficiency is a very important tool for decarbonization, but you can only go so far because of practical limitations with energy efficiency. So there are other things that we also need to do if we want to get deep decarbonization. And we have three speakers this morning who will be talking about two of those techniques for decarbonization. And I'm not going to spend much time talking about them. There's a lot of information on our website if you visit there, and the address for the website will be put into the chat. So you'll be able to visit the website to get information on the speakers and also on their topics. Moving on. The Energy Forum will be followed at 6 o'clock by the South Texas Section American Institute of Chemical Engineers monthly meeting. And all of you on this forum are welcome to attend that also. The speaker will be Faisal Khan, the new director of the Mary K. O'Connor Process Safety Center at Texas A&M. And you will be speaking about, well, obviously process safety. So you're welcome to stay for that at 6 o'clock. Also, I'd like to acknowledge the two sponsors for the AICHE meeting, TLV and Atlantium Technologies. TLV is a longtime sponsor, and many of you, I'm sure, are familiar with them. They're a steam specialist company and probably best known for their steam traps. And Atlantium is a new sponsor. They specialize in UV technology for water treatment used for dechlorination and purification of the water. So if you want more information on them, visit their websites. And then finally, just a couple of housekeeping notes here. First of all, please stay muted and keep your video off during the presentations. Secondly, there will be certificates of participation for professional development hours available at the end of the Energy Forum, and again also at the end of the AICHE meeting. The link that you see here, and again this will be placed into the chat for you to use, will take you to a screen which is shown on the slide, which will allow you to press on a button, click a button, which will then take you to the PDH application form. So if you want to request a PDH, you will have to follow through these links and select the appropriate PDH that you're looking for. And then you'll have to provide your email address, phone number, and also verify that you've attended the session in its entirety, and then you can claim your PDH form. So hold on to that for the end of the session. And then finally, for the Q&A, we do have a link here that you can use for that. Please do not put Q&A into the chat. Please use this link that is shown on the screen. And again, that should now be shown up. There should be this link in the chat as well, so you're able to copy it from there. If you want to send a message, if you want to send a question for Q&A, please use this link to do it. All right, I think that's all I really have to say, and I'd like to save as much time as possible for our speakers. So I'll just briefly introduce our first speaker, who is James Turner from Fluor, Executive Process Director at Fluor, and I will hand over to him to give his talk on decarbonizing industrial process facilities by electrification. James.
Thanks, Alan. Let me see if I can share my screen here.
Looking good.
Okay, everybody looking good? Okay. Thanks for the introduction, Alan. There are several strategies that can be pursued for reducing carbon emissions from industrial facilities and from the products they produce. Energy efficiency can certainly be one of them. Let's see if I can page down here. There we go. But as noted by Alan Rossiter a few minutes ago, there's just only so far you can go with energy efficiency. Carbon capture is also certainly a key possibility. Making and using green fuels, such as battery-operated vehicles with green electricity, hydrogen, blue or green, renewable diesel, and fuels from renewable feedstocks such as biomass can also reduce emissions. Materials recycling can also play a role. It's clear there's not just one winning strategy. A combination of all of these strategies and more will be required to achieve the goals. Today, I'll be talking about electrification of industrial facilities and how this can also be a key component in a decarbonization plan. Electrification simply means designing new or revamping existing facilities to use more electricity instead of steam and fuel gas for your energy needs. It's pretty easy to document how electrification can reduce a facility's carbon footprint. Electricity producers calculate a carbon footprint per kilowatt hour, so that can be directly compared to the carbon emissions that a facility produces to make the steam or burn the fuel that would otherwise be used to provide their energy needs. Before I get into the details of electrification, I want to briefly highlight potential other advantages to electrification in addition to reducing carbon emissions. So I'd like to ask a few rhetorical questions. Is your facility operating at its peak energy efficiency? Many operators see a noticeable improvement in their energy intensity index from electrification. The calculations are based on efficient electricity production compared to less efficient steam boiler production. Are your steam generating systems and turbines becoming obsolete and requiring ever-growing maintenance needs? Owners may have steam boiler maintenance and equipment replacement or emissions requirements that will require investment. Some of this investment may be better spent on electrification. Overall reliability may increase, which can have a big impact to the bottom line. Are you looking for ways to reduce NOx or other emissions for local regulatory compliance? You may be facing looming environmental regulations that will require investment in new SCRs for your steam boilers. An electrification project can reduce your steam demand, therefore reducing the cost of environmental upgrades. This can be even more significant when you consider that emissions reductions from electrification may fit well with other strategic plans that could cause increases in emissions from process heaters. The emissions reductions in the steam system can be used to offset increases in the other heaters. It's not just about NOx. SOx and particulate matter emissions can also go down, producing credits that can be valuable for your other strategic goals. Are your utility systems maxed out or worse, out of balance? If you have limitations on your steam balance, cooling water balance, or natural gas import, you may not be able to expand or do other projects without doing some electrification. Can you purchase electricity for a lower cost than import natural gas? If so, this can also reduce your operating costs. You need to rebalance steam and electricity usage, but are concerned about what to do with excess fuel gas. There are potential synergies in executing an electrification project with a project to increase LPG recovery from the fuel gas system. Burning less fuel would already mean that you're making less CO2. But by recovering more LPG and heavier material from your fuel gas system and replacing it with import natural gas, you'll further reduce CO2 emissions, even if your fired heater duty did not decrease. In most markets, LPG products and other liquid products are more valuable than replacement natural gas, so there can be a good benefit to the bottom line in addition to the CO2 reduction. Does a facility-wide energy optimization sound intriguing, but also intimidating? If you're planning a strategic reconfiguration based on shifting crude supply and/or market-driven product changes, that may be an opportunity to replace aging steam-driven compressors with new motor-driven compressors that have a fit-for-purpose duty specification. Some regions are offering significant credits for facilities that reduce carbon emissions both directly from their facility, and in some cases, including the emissions from the end user of their products. One example is the LCFS credits in California. LCFS credits and other carbon reduction incentive programs can have a large impact on your project economics as you seek to improve your plant efficiency and reduce carbon emissions. For any project, capital cost is an important factor, but there are other factors that should be considered so that you know all the impacts to the project are understood and accounted for. Any electrification project is likely to have secondary impacts to your utility systems in addition to the direct impacts. We've helped several clients with this effort on past projects. Some challenges may appear overwhelming at first, but we can help untangle the string so that all the impacts, both positive and negative, to your systems are understood. For a project where steam supplied energy is being replaced by electricity, the obvious impacts are to the steam system and the electrical system. For steam, there's less overall steam demand if steam drivers are replaced with motors. However, it's important to understand the total impact to your steam balance at the various steam levels in your facility. Specifically, if you're long on low pressure steam and have back pressure turbines that produce a lot of this low pressure steam, replacing those drivers with motors can be a big benefit. Conversely, if you need all of the low pressure steam created by a back pressure turbine, replacing it may not have much value if you would then need to let down more steam across a control valve to balance your needs. There may be significant impacts to other utility systems as well. The fuel gas system will frequently be impacted. If fired heat is being directly replaced by electricity, that's a reduction in fuel gas consumption. Likewise, if steam is replaced by electricity, that will end up reducing fuel gas consumption at the steam boilers. The water system can also be greatly affected by an electrification project. If you replace condensing steam turbines with motors, this may have a significant reduction in cooling water demand, debottlenecking this utility and reducing water makeup to the cooling water system. So what are ways that industrial facilities can electrify? There are three primary ways to be considered: heat pumps instead of reboilers and condensers for distillation columns, electric heating instead of steam or fuel-fired heaters, and electric motors instead of steam turbines. All three of these can be important and have large impacts in the right situation. A fourth concept is utilizing a cogen type facility to produce electricity and steam instead of using import electricity and producing steam in boilers. So let's talk about these three items in a little bit more detail. I'll start with the first one, using a heat pump designed to power the reboiler and condenser in a distillation column. Historically, these designs have been called heat pumps. They're also called mechanical vapor recompression, or MVR. Heat pumps use a compressor to compress the overhead vapor from a column to a high enough pressure that the condensing temperature is above the temperature required to reboil the bottom of the column. Then the compressed vapor can be used as the heat source for the reboiler. Shown is a simplified sketch of the concept. Heat pumps can have a significantly better energy efficiency than traditional reboiler condenser systems and save on both the reboiler side, which is often steam, and the condenser side, which is often cooling water. Energy intensity reductions of up to 90% are reported in the literature. Heat pumps work very well for systems that don't have a big temperature difference between the top of the column and the bottom of the column. Propane-propylene splitters, ethane-ethylene splitters in steam cracker units, and isobutane normal butane splitters are a few examples of this type of column. For most other distillation separations used by refineries and petrochemical complexes, the much larger temperature change across the column significantly reduces the value of the heat pump approach and makes it impractical. This idea appears to be best suited for a new design, as it would be a major revamp to retrofit an existing column with a heat pump. Looking at the scorecard of impacts, this idea can reduce fuel, steam, and water consumption, reduce emissions, and improve efficiency with the cost of higher electricity demand. Now let's talk about the second item. For steam heating needs, there are two ways to electrify. Either replace a steam heater with an electrically heated exchanger, or replace a fuel-fired steam boiler with an electric boiler. Shown on the right is an electric heater. Steam and condensate piping and controls are replaced by electrical supply, which may reduce maintenance expenses and reduces capital costs for a new facility. One advantage of a steam exchanger is the maximum temperature is self-limiting. You can't heat the process up to a higher temperature than the condensing temperature of the steam. An electric heater will not have this same intrinsic feature. Controls must be designed to provide protection against overheating the process for upset, low flow, and blocked-in scenarios. Like the heat pump, this concept can reduce fuel, steam, and water consumption, reduce emissions, and improve efficiency with the cost of higher electricity demand and potentially less temperature controllability. Shown on the right is an electric steam generator sold by Stork. It may be a good option for a revamp of an existing facility. You can reduce your current emissions from steam generation while still supporting all of the existing process needs with steam. Note, many processes use live steam injection into the process, so it's not practical for these to replace all your steam needs directly with electric heaters. This is an advantage of an electric boiler. It can address steam injection and steam heating needs. This concept can reduce fuel consumption, reduce emissions, and improve efficiency with the cost of higher electricity demand. Now I want to talk about the third idea on the list, using electric motors instead of steam turbines for large compressors and pump drivers. If replacing a compressor driver makes sense, you may want to also consider if installing a whole new compressor is a good option. If there's adequate plot space available, installing a whole new compressor with an electric motor may not cost more when the cost of doing work during a turnaround versus new construction outside of a turnaround is considered. This can allow you to replace an aging compressor with a new compressor and potentially optimize it for your current operation instead of the way the unit was operated decades ago when the compressor was originally specified. However, consideration is necessary when changing to electric motors that you understand the full impact on compressor operation. This driver change may also impact release scenarios and flare loads. Looking at the impacts, this idea can reduce fuel, steam, and water consumption, reduce emissions, and improve efficiency with the cost of higher electricity demand. One item that needs to be considered when replacing a steam turbine driver with an electric motor for a centrifugal compressor is the potential impact on the operating speed. Shown here is a typical compressor curve that can operate at different speeds. Steam turbine drives have an inherent ability to change speeds, which can provide more flexibility and operability for the compressor to manage changes in mole weight and flow requirements. When replacing a steam turbine with a fixed speed motor, this impact needs to be carefully considered. Suction throttle valve and spillback valves may need to be modified or replaced to provide the flexibility that was previously provided by varying the turbine speed. Installing a variable speed motor is, of course, an option, but for large motors, there's usually considerable additional cost and space required. A better option may be to install a variable speed gearbox to convert the fixed speed motor to different speeds as required to optimize the compressor operation. These issues can almost always be addressed, but they need to be considered. I talked a bit ago about the high-level utility impacts. Now I'd like to go into a little bit more detail on a few of them. Electrification can have a big impact on the steam balance, which can have a big impact on the fuel balance. Replacing a fuel-fired heater with electric heaters will also have a big impact on the fuel gas balance. Many refiners run close to fuel balance and would be long on fuel gas if they do the electrification that they want to do. If this is an issue, there may be options for recovering more LPG and heavier material from the fuel gas pool, or possibly to make less material that ends up in the fuel gas system. Projects to increase C3+ recovery in gas plants have a very good payout in selling more LPG product and also support efforts to electrify. If this option is pursued, product storage and transfer logistics will need to be understood so that all requirements are addressed. You may also be able to reduce your fuel gas system by making changes in conversion units so that you crack less and make less material that ends up in the fuel. If you reduce the amount of LPG in your fuel gas, you'll need to understand how this can affect the heating value of your fuel gas. Replacing LPG with methane will lower your heating value, so you'll want to know if you have any heaters that would have fuel gas hydraulic issues with a lower average heating value. Here are a few examples that show the potential impact of replacing a steam turbine driver with an electric motor to the electrical, steam, fuel gas, and cooling water systems. There are two main types of steam turbines, condensing and back pressure. There's also condensing turbines that extract steam at one or more intermediate pressures. Condensing turbines exhaust steam at a vacuum, and the steam is then condensed into water, usually in cooling water exchangers. Back pressure turbines take a relatively high pressure steam, say 600 psig, and exhaust at a lower pressure, say 150 psig. Since there's much more energy in 150 psig steam than steam at a vacuum, a much larger steam flow rate is required for the same driver load for a back pressure turbine compared to a condensing turbine. Back pressure turbines are a good fit for a facility if there's demand for the low pressure steam. However, if your demand for the low pressure steam has changed over the years, an existing turbine may be producing a lot of steam that you really don't want. This can provide a good incentive to replace that turbine with an electric motor. Another option could be considered is installing or expanding a cogeneration unit. These units convert fuel into electricity and a heat source, typically steam. These systems are now often called CHP, or combined heat and power. Installation of a new CHP is a significant capital investment, and one key factor in this decision may be if an existing boiler requires significant updates to meet modern emission requirements. As previously mentioned, if a facility has plans to replace a significant amount of steam consumption or steam generation with electrical energy, it may be long on fuel gas. A new cogen unit could become a sink for this produced fuel gas. To address the carbon emissions impact, you can add a carbon capture system to the cogen, and that'll take care of that issue. A design for a new facility can use any of the ideas that we've discussed for revamping existing facilities. Are there other ideas that could be used for a new facility that may not be practical for revamps? A lot of people are looking into this. Let's take the example of a naphtha steam cracker that produces ethylene, propylene, and aromatics. Reactions take place at high temperature, typically about 850 degrees centigrade, and it's an endothermic reaction, so you need to add a lot of energy to keep the reaction going. Existing steam crackers have a large fuel gas heater to supply this heat. Could these heaters be replaced with an electric heater? We've done some calculations. For a typical naphtha steam cracker that makes 1,500 kTA of ethylene, 1,400 megawatts of absorbed duty would be required to provide the reactor heat. So this unit would require electrical consumption similar to what many large commercial power plants produce. So this may be technically possible, but it will be expensive. If your goal is to produce steam cracker products with minimum CO2 emissions, there may be some other options. One option would be to use a fired heater, but use hydrogen as the fuel. Calculations indicate that 460 kTA of hydrogen, or 530 million scus per day, would be needed. It's also technically possible, but costly. It may be possible to revamp an existing unit that uses fuel gas as heater to use hydrogen, but this would likely require infrastructure and fuels controls changes. There's a third option that may be the best choice. Use fuel gas as is done in all steam crackers today, but capture the CO2 from the flue gas. This technology is available today. In fact, Fluor licenses such a technology, the Economine FG Plus process. Of course, you need to have a disposition for the recovered CO2 for this option. With the first and second option, the major issue is, what do you do with the methane produced by the steam cracker process? Steam crackers produce a lot of methane as a side product. In existing units, this gas is burned in the process heaters. If the heaters are electric, this methane needs to be used for something else. There may be synergies with the steam cracker combined with GTL or gas to liquids process, convert the methane into a liquid product, or possibly with a syngas operation to make methanol or hydrogen. In summary, there are ideas and options available, The best choice may depend on what your goals are and on location logistics. So how can an operator determine what to do? Develop an accurate power, steam, and fuel gas balance for the facility. Consider upset and other operating cases, such as when individual units are shut down for maintenance. Understand the reliability of the existing systems and what outages can have a big impact on the operations. Are there steam boiler replacement or reliability improvement projects being considered? You may be better off figuring out how to decrease steam consumption instead of spending money to make your current system more reliable. Understand your cost for incremental purchase power and import natural gas. You'll need to understand what upgrades of the system within your facility will be required, but also be aware of possible infrastructure impacts to your across-the-fence electrical supplier. Understand what current and future emissions requirements may have on your facility. These requirements could be both regulatory driven or internal company requirements. In conclusion, to find the best project for your facility, you should start with high-level goals, develop a good understanding of where you are, compare options, understand which parts are independent and can be evaluated individually, and which parts are interrelated and need to be considered as a group. You'll want to understand the benefits: reduction in carbon footprint, reduction in operating costs, improvement in energy efficiency, reduction in other emissions and in water consumption. And of course, you'll need to understand the cost, the capital cost to implement changes, systems upgrades required both within your facility and by outside suppliers, the process ISBL and OSBL impacts, both positive and negative, for each option. After all, it doesn't help you if a preliminary study makes an option look promising, but impacts that were not initially considered make the option much more expensive or not practical. Finally, I'd like to mention that there's a more detailed webinar on electrification and also some on carbon capture available on the Innovation Builders page on Fluor.com. Fluor has a long history of helping our clients perform these types of studies. We have the experience, tools, and expertise to help look under every rock, both to find hidden opportunities and to discover all the impacts, both positive and negative, for each option. If this sounds intriguing to you, please contact us and we'll discuss your specific situation and how we can help you find the right solution. With that, I'd be happy to address any questions or comments that you may have.
Thank you, James. We do have a couple of questions that have come in that I can pitch away. Let's start with these. So one of our questions related to your discussion of MVRs, mechanical vapor recompression. And the question was, how are they controlled in upset conditions? Is there good technology there to manage that?
Well, obviously you would need a control system. This is not a new technology. These systems have been used, heat pumps, for many years. And so I think there's controls that are understood to be able to manage that. I'm not aware that that's a reason to not consider going with the heat pump type approach.
How common are they in your experience?
Well, in certain applications, they're very common. The applications that I mentioned, propane propylene splitters and refineries and chemical plants that are doing that, it's very common there. And ethane ethylene splitters and steam crackers, it's fairly common there. Okay. There's not a whole lot of applications, just because most of the columns and refineries and petrochemical plants, you have a much wider temperature range between the top of the column and the bottom.
Sure. One other question that came in related to electric heating. What limitations do you have on that in terms of heat flux and maximum temperature that you can achieve?
I have that information, but I don't know it off the top of my head. I could provide that later.
Okay, one other one that I'll just pass on to you quickly, and you slightly touched on this in some of your discussions, but on cost economics, basically, both in terms of capital cost and operating costs, how attractive in general are the electric options compared to the current options for processes?
Well, it depends. I would say that historically there's been some projects where people look to replace steam turbines with electric motors. The first one I worked on was over 20 years ago and was for a refinery in Louisiana. So it did not have anything, they weren't looking to reduce their carbon footprint at that time and weren't getting any incentives for it other than they could buy natural gas cheaper than they could buy electricity cheaper than they could buy natural gas. And it also helped their steam balance because of the way that it fit with their, it was a back pressure turbine. And I think the projects that we're looking at now, the economics look very good because there's environmental reasons that would cause them to upgrade their steam boilers anyway. And so they're able to take some of that money that would be otherwise used to either add SCRs to their existing old boilers or build new boilers with SCRs. And so they can save money on that and use that for electrification, as well as get some government incentives for the reduced carbon footprint. Great,
excellent. Very good. Thank you so much for your presentation. A lot of useful information there, and I'm sure we'll have more questions, but that's all we have time for right now. So thanks so much. Yeah. All right. Let's move along, and I'll introduce our next speaker, who is Jack Farley, who will be speaking to us about green power supply in Texas. And I will stop sharing here. And I think, Lee, if you could put the slides up for Jack, that would be great.
Thanks, Alan. I was pretty excited when Alan called me a couple months ago to talk about how you can use green power supply to reduce costs to industrial facilities and get that delivered from the ever reliable ERCOT grid. Then a week ago, Alan called me back and said, "Hey, Jack, in addition to talking about reliable green energy from the Texas grid, can you also talk about the freeze event?" And so let me start there, and I'll take a few questions, then we'll talk about green power supply. So if you go to the first page, Lee, this is the biggest, by far, reliability failure in the history of Texas. Nothing comes even remotely close to this. And we're going to start by looking high level at the demand side of the equation. We had all-time record low temperatures that I'm sure you on the industrial side and us on the power side never put into any planning model. They were beyond the tails of the distribution. In fact, ERCOT was projecting a peak load of a little over 77 gigawatts on Monday of the freeze, the 15th. And the peak load we've ever served is 74 megawatts in the summer. So this was above and beyond anything we've ever seen before. And on the right is the hourly load forecast in purple. We never actually achieved that forecast because of load curtailment, but had we achieved it, it was about almost 47% higher than last February. Give you a sense of the magnitude of how much higher it is. And about 5% higher than the record all-time peak set in two summers, last summer and the summer before. Having said all that, when we served those previous record loads, we got through it. There was no load shed, no involuntary load shed. And we actually, the grid could have handled the 77 gigawatt forecast had it had a very healthy supply system, which we didn't have. So we'll go to the next page. The real story was the supply side for the freeze. That's where the failure occurred. And I'll describe the graph on the left first. This is the thermal and renewable outages that occurred across the week. The green is the renewable outages. The gray is the thermal outages by hour. You can see that we were approaching Monday, the 14th and 15th with a little above average. The black line is last year's outages for February, total outages. So we were about 10 gigs high, which is not good, but it's not you know, if we held it 10 gigs high on the high side, we could have gotten through this with a lot less pain and curtailment. But then the outages shot up around 1 a.m. on Monday. So what drove all this? And you've seen press reports, and I've seen them all. They give bits and pieces. The full picture will come out later when data on every single plant is available. Right now, we have sketches from different owners. And what you found, you know, based on what's been released so far is, you know, did power plants break? Yes. Did power plants freeze? Yes. Did wind turbines freeze? Yes. But, and those things can happen, and they always will. But two other things happened that were very unexpected. And I certainly, you know, after almost 30 years in the power business, I didn't see these coming. And that is, number one, that the gas supply system essentially went down. We had low pressures on the gas pipeline systems that serve most of the power plants in Texas through almost the entire week. There were power plants that purchased gas at prices that were 10 to 30 times higher than normal. So they paid ridiculously high prices, but the gas was unusable because the pressure was at a level that was not usable in the combustion process. Most gas turbines need between 500 and 1,000 psi inlet pressure to enter the airstream in order to support combustion, and the pressure just wasn't there. Why wasn't the pressure there? We lost 10 BCF a day of supply from freezes, as well as shut-ins where gas suppliers resold their power supply, their power that they were using for methanol injection and in production, and compression and other production processes in order to make $9,000, because that was the price of power. So we actively had, you know, supply suppression due to the power price. We also just had freezes on the supply side. We also suffered problems on the pipeline system, electric compression that froze, and electric compression again, where the power supply was resold because there was a better economic incentive from selling power that we were going to use for compression instead of using it to keep the pipeline pressures at adequate levels. I never saw that one coming. That was something new and different that's, you know, had never really happened on the grid before. The second thing we didn't see coming was frequency and voltage problems. And this knocked out a number of units. And you might say, well, wouldn't you expect frequency and voltage problems during an event like this? The answer is no. I mean, the grids are trained and built to manage involuntary load shed, keep a margin of safety, keep all their resources at hand that they use for frequency management and voltage support. And they should have been able to load shed and still maintain a very consistent frequency and voltage in the system, but ERCOT didn't. And as a result, Monday at about 1 a.m., we lost 9 large units for frequency and voltage problems that tripped for safety purposes, which is unprecedented. Never seen that type of, you know, unit outage, you know, event, other than an uncontrolled blackout, which occurred in 2003 in the Midwest. So those were two big contributors beyond just, you know, freezing plants and freezing wind turbines. In fact, I think when the dust settles, I'd be willing to bet that the natural gas deliverability was the biggest issue that we faced. Now, the other issue we faced was we have a construct in Texas that says we're going to incentivize the power producers to make all the power they can by paying $9,000 in scarcity events. That's about 300 times the normal price of power. Unfortunately, that very real-time incentive, a very strong incentive, can do nothing to fix a frozen generator, lack of gas pressure, or frequency management problems by ERCOT that are making units trip for safety. It just has no effect whatsoever on those issues. So in real time, it didn't help us. Bottom line from this is the problem that we faced probably could have been managed a lot better. Maybe even no load shed at all, but probably more of a small load shed would have been adequate. But the extra problems we face because of gas supply and frequency and voltage management just made it a big failure. I'll stop there, Alan, and take a couple of questions if you'd like, or we can move on.
Yeah, sure. I'm not actually seeing any questions in the question box at the moment, but from my side, I mean, I realize there's still a lot of information to come in. I mean, how much, we're hearing a lot of controversial discussions out there.
Mm-hmm.
How much of this do you see as a technical failure, the equipment per se, and how much of it do you see as a management and oversight behavior, failure rather?
Yeah, that's a great question. I don't have the answer, but the management failure and the management of the grid by ERCOT, particularly on Monday at 1 a.m. in the morning, we had the biggest frequency drop that I think anyone's ever seen in an ERCOT grid. I mean, twice as big of a drop that I've ever seen in the last 10 years. That was a big contributor, and it shouldn't have happened. The coordination issues between natural gas and power, where the gas market, the pipeline operators, the gas producers were getting signals to not use power, were getting interrupted involuntarily, that reduced the supply potential to fix the problem. That shouldn't have happened. That should have been coordinated, should have been planned for better. It wasn't. So maybe it's 50-50 between freezing technical issues and bad management, something in that order.
There was a comment here from Gary who says, would the ability to declare force majeure and mandate that all suppliers of fuel and electricity meet the priority needs? Is there a mechanism, or should there be a mechanism to do that? You know, if the governor declares a state of emergency, for example?
I think there should be that mechanism for sure, Alan. I think the week before this event, I'll just tell you, most people in the power sector like me were expecting almost 100% probability of a blackout, a controlled load shed. I shouldn't call it blackout, but a small one. So this was foreseeable. And I even felt, and I think a lot of people did, that the Texas Railroad Commission, the PUCT, and the governor made some moves, but they weren't real strong, you know, like, hey, we're pulling out all the stops kinds of moves. And I think it's, again, no one has planned for this scenario because nobody saw this kind of cold weather ever before. And I think it just caught us, you know, a little off guard.
Flat-footed. Yeah, sure.
Yeah.
Okay, well, thanks very much. I know there was something very current affairs, and I'm glad you were able to touch on that. But now I did originally invite you to talk about green power supply, so let's have that part of the talk. Thanks so much.
Let's do this, and we'll look forward here a little bit. So, if you're considering, you know, green power supplies from the Texas grid in the future, near future, midterm future, let me just hit on a very brief period of time on the most important factors and trends, and we'll start by looking at what you're kind of faced with fundamentally, which is these graphs. So these graphs depict on the left, they depict your average production profile for Texas solar, West Texas wind, and coastal wind versus the gray line, which is your average profile for demand. Now your plant might have a different profile. This is an average Texas profile. And you can see these things don't line up on a monthly basis, okay? On the right, it's the exact same analysis, except it's per hour of the day. So this is the average profile for, you know, 1 in the morning, midday, all the way to midnight. Again, they don't match up, and they never will, which is going to leave you, if you procure green supplies from a new resource like a wind farm or, you know, solar park for your industrial facility, which is a very good value, by the way. I mean, it's one of the cheapest ways to buy power on the grid today. If you do that, though, you're going to face hours where you don't have enough supply and you have to buy from the grid. And generally those hours, the prices are higher. You're also going to face hours where you have too much supply from your renewable resource versus your load, and you're going to have to sell power to the grid. And those hours are generally the lower priced hours. So let's talk about how you will think about and take advantage of that dynamic. Next page, please. The biggest change in the Texas grid over the last 10 or more years is the tremendous growth of wind and solar capacity on the grid. The graph on the left shows you how much new capacity was installed each year for the last 6 years. In 2020, we installed 7.7 gigawatts of wind and solar. That's that's $9 billion of investment. It's a lot. In that same period, we had a net reduction in thermal capacity on the grid. But between retirements and new build, we had about a 6 gigawatt reduction in dispatchable thermal capacity. So renewable additions and renewables taking over the supply scene is the picture in ERCOT. On the right side is the percent of all power produced in per year that came from wind and solar. And you can see from 2015 to 2020, it more than doubled from 12% to 25%. Now, this is great from perspective of decarbonization and carbon intensity. The carbon intensity in Texas has been going down fairly significantly because of this, as well as the retirement of about 5 gigawatts of coal. So that's good. But what does this do to your risk of owning green supply? The next page. To figure that out, we created a very simple future scenario where we add 2.5 gigs of wind and 2.5 gigs of solar per year with ERCOT load growth and all the other ERCOT fundamental parameters around hourly shapes for load and wind and solar production, and then various other factors. And we look at how the grid will change on an hourly basis. And at a high level, on the left, you see that renewable penetration can go from 25% to 58%. Again, this is not an aggressive scenario. This is less renewable additions than what we've actually experienced for the last 2 years, a little bit less. So fairly middle of the road scenario. And on the right, you see how this affects average energy supply across the period. The green and yellow wedges for wind and solar get a lot bigger. The gray wedge, which is your nuclear, coal, and natural gas dispatchable units, gets a lot lower. What does this mean in terms of price? Well, the gray units, the wind or the nuclear, coal, and gas, set the price in Texas. They set it using what's called net load. Net load is our total load on the system in an hour minus the renewable production, because the renewable production comes in at 0 or less price to the grid, to the market. So what's left over to serve by dispatchable units is called the net load. And if net load is low, prices get lower. If net load is high, prices get higher as you climb a supply curve of resources. So a declining average net load that you see here is going to mean declining power prices, but for an occasional weather spike or maybe natural gas prices spike. With weather normal and no change in gas, prices will go down on average. But here's the most important thing I want to tell you. You cannot look at the Texas grid at an average level, okay? You will miss what's really important underneath that at the hourly level. So Lee, go to the next page. Now we'll look at the hourly level. There's 4 graphs on this page. They represent years from 2020 to 2035. On each of these graphs are 8,760 dot points that represent the hourly net load. On the y-axis is the actual load projected either in 2020 actual or projected in the future. On the x-axis is renewable production. The net of these is the net load. If you look at these clouds of dots, they get wider and wider and wider. And you'll see that the horizontal range quadruples. That is the range of renewable production on any given hour. It becomes explosively large and becomes a much greater variability factor than load, which was traditionally our biggest factor we dealt with on the grid. When you look at these, you can see three major trends, which are in the box to the right. The first, the biggest trend, is that the number of dots that are below those blue diagonal lines grows from about 5 to 10% to 40 to 50% of all hours. What do those mean? If you have a net load below those blue lines, it's a very, very high probability that the market price will be zero, free electricity. And we are looking at a lot of hours where the price is going to be zero with this scenario, which I think is a fairly likely scenario. So that's point number one, a lot of hours with very low prices. The second point is if you look above the red and green, the red and orange lines, you'll see a number of dots, not a lot, but a number of dots. And the magnitude of those dots doesn't change. Those are the high net load periods where we're going to have scarcity. This is where prices could be several $100s to $9,000. And the magnitude doesn't really change. And this is a little counterintuitive because people think, oh, if we add a lot of solar, we're going to knock down the peaks and there won't be any problem with, shortages on summers and stuff like that. Well, it's not true. What happens, and this has already happened in California, and it will happen in Texas as well, is the solar knocks your peak net load out of the sunshiny hours of 5 and 6 o'clock at night, but then your non-sunshiny hours of 7 and 8 o'clock at night in the summer become your new net peak loads. And so that shifts the peaks out into those hours, and that's where we're going to have volatility, as well as, of course, winter events in those same sundown hours. The last big trend is you get a lot more what we call ramps in the power business, where the net load shifts between 1 hour and the next in a dramatic fashion. We're going to be looking at about 15 times more extreme net load ramps of about 5 gigs in the future, which will create a lot more price volatility. Okay, so that's the fundamental trends. So how do I think about my renewable portfolio strategy? Well, first, next page, Lee, before you start working on your strategy, I have to ask you to please look at your demand of your industrial facility and see, can I be more flexible in using electricity? Can I interrupt the whole process, part of the process? How long can I interrupt it? The value of interrupting at ERCOT has already gotten very large, and it will only get larger in the future because of the trends I just showed you. If you can avoid those high net load periods, but take advantage of all the low net load periods, you'll have very cheap power. This graph here shows you the average price of wholesale power from 2016 to 2020. The bar on the left of each year is if you had no interruption in your demand. You just took power at the same level the whole year, every hour. The bar on the right of each grouping shows you if you could interrupt 10% of the time, obviously the 10% of hours that have the highest price. The amount of savings, it ranges depending on the prices and the volatility in a given year, but the savings can be as high as 30% of your entire power bill if you can interrupt 10%. The savings, even if you can only interrupt 1%, which is the second bar, the savings are really large on the wholesale side. And again, I believe, given the trends on renewable penetration, these savings deltas for interruptions will just get bigger and bigger. Lee, can you go to the next page? Your savings from flexibility don't stop at wholesale power. They go on to transmission, which is the second biggest part of an industrial's bill. and it's a large part. And this graph on the left shows you the amount of transmission costs that are being recovered by the ERCOT loads each year. And that cost is going up rapidly. Most of that cost driven by interconnecting new wind and solar facilities, but also, interconnecting new loads and building greater capacity for load growth. But nonetheless, the cost is going up. If you're a transmission interconnected load, your average cost for baseload electricity in Encore and AEP are depicted by these dark blue bars on the right. About, call it just a little less than $9. And again, that's today. And again, that number probably goes up in the future as we continue to add more transmission. If you're able to interrupt your facility less than 1% of the hours of the year, well less than 1%, you can chop 60 to 90% of that cost out by avoiding what are called the 4 coincident peak hours in June, July, August, and September. That's just part of the tariff design in Texas for transmission customers. And if you can avoid taking part or all of your load, whichever part you can avoid in those 4 CP hours, it's called the 4 CP, you can reduce your transmission bill significantly. And it's the same for CenterPoint and other parts of Texas as well. So before you do your strategy, please look hard at your flexibility on the demand side. I'll also just make another comment here that the Texas grid continues to add opportunities for the demand side of the market to participate in the market, to provide flexibility to the market through ancillary services, to provide energy back to the market, even if you're at distribution level. So the flexibility will become more accessible to the market, and the value, I think, will grow dramatically. That leaves us with now the strategy, the next page, Lee. Yeah, there's a lot of things that beyond wholesale power and your transmission bill to think about, but the other things are smaller magnitude for sure. There's congestion risk between where your wind gets delivered, your solar gets delivered, and your plant. That has a lot of complexity on how you manage that. There's the ancillary services that you have to provide as a load entity. You're obligated to provide a chunk of those. They cost about $1 to $2 a megawatt hour. There's whether you're going to self-provide your scheduling and retail electric provider services. I'd say if you're an industrial with a load of more than 25 or 20 megawatts, you could certainly think hard about providing those services instead of going through a third party and paying $1 to $5, and do it in on a scale, a reasonably decent scale cost. And then lastly, credit support, because renewable contracts require a lot of credit to the renewable owner. They also require credit to ERCOT as you execute those agreements, and you require credit with third parties as you manage hedging in and around those agreements. Quite a bit of credit involved. And then lastly, if you're not a large industrial, maybe your load's less than 5 megawatts, you could consider bundled services from an REP. Like NRG has a program where you can have dedicated renewable asset that gets built partially for your load, and they wrap all the risk and the services around it and give you a fixed price bundled supply. So those are kind of the things to think about on strategy. I think I stayed under my time limit, Alan, and I'd be happy to take some questions.
Very good. Yes, that was quite a race there to get there, but yeah, very interesting stuff. Just to put one thing in perspective here, obviously we had James talking about electrification inside the refineries and chemical plants and so on. You've talked about the renewable energy supply, and of course, while you can achieve decarbonization inside the plants by using electricity, if you don't have a renewable or a decarbonized electric source, you are not net saving. Doing any decarbonization, or in most cases, you would not be getting that benefit on the carbon side. So that's really why we had these two talks. And I guess I should have said that up front, just to put these two in context.
Correct.
Okay, very good. So there were a couple of questions here which actually are sort of overlapping between what you said in your first part of your presentation and the second part, but these were in the chat here. A couple of people asking about 4CP timing and can you predict them? And then the second part of this is, will there be 4CP times in the winter, do you think, based on recent experience?
That's a great question. On the first one, timing, there is some guesswork involved in, when are the coincident peaks going to occur? You're sitting in July and it gets really hot in July 4th. Is that going to be the peak for the month, or is it going to happen again later on? And certainly that's, people have to kind of jump around and cover more than they have to. I will tell you, you can pretty safely cover the 4CP hours with no more than 60 hours of interruption, which is again less than 1% of the hours of the year, probably even 45. So you don't need a lot of interruptions to make sure you hit the correct hours each year. Second part of the question, what about winter 4CP? Well, it's not part of the tariff design today. They do not make you interrupt during the winter. I suspect, in fact, I would probably bet money, Alan, that the 4CP will be extended to the winter months. So they'll, instead of just 4 months of interruption in the 4 coincident hours, there'll be maybe a 12CP or an 8CP where there's 8 months or 12 months.
Okay, very good. And one other question, and then this probably will have to be the last one because of our time constraints, but this related to energy storage, and a couple of people have asked in this field. So obviously this volatility, price volatility is largely around variability of available supply. How big a factor do you feel energy storage is going to be in the coming years within the ERCOT system? And what forms of energy storage?
Oh,
maybe I shouldn't have asked you that question, but
that's a great question. Thank you, Alan. Well, I'll tell you, I have a biased, full disclosure. I developed long duration energy storage. It's called compressed air energy storage. That's my job. And it's 48 hours of storage duration. I think, and it's economically viable right now. Even without the freeze event, it's very economically viable. And in fact, I'll just throw out a little tidbit. During the freeze, had our plant project been up and running, which is not, had our project been running, we would have had a 3.5 day payback on all the capital to build the project.
Wow.
It's pretty crazy. And we would have managed to get through the entire event without having, with enough inventory to make it through the whole 4.5 days of the emergency event. On the flip side, there's a number of 1 hour batteries that have been added in the last 18 months in ERCOT, about like 300, 400 mags worth. They had a terrible freeze event. In fact, I maybe, run them out of business kind of freeze event, we'll see. But the problem was the use of the ancillary services that these batteries generally provide went way up, and they required a lot of energy, well beyond what the inventories of these batteries were designed to accommodate. And they had to withdraw from the market for most of the event. So that was a tough deal. Now, batteries are going to get cheaper, and then you can have longer duration in the future at a lower cost. That will definitely help. Our technology will get cheaper, but I think storage will come in a little bit slower than the wind and solar. Wind and solar just has such a tailwind. People love it. The Googles and Amazons buy the heck out of it.
Right.
The capital market loves it. So it's just hitting and hitting and hitting. And I think it'll take a while for the energy storage, the capital markets and the hedgers and everybody else to kind of reach the level we see in wind and solar. Years.
Very good. Just one last question, and then we'll have to move along. I'm just slipping this one in. Another one that came up here was this $0 price that you mentioned. Is that due strictly to renewables, or are there other causes for that?
That's a great question, Alan. It's not strictly due to renewables. In fact, so we have an average load in Texas of about 35 gigs in an hour. It varies across the year, obviously. There's about 15 gigs of dispatchable units that bid in below zero. They're called price taking units. Some of them as low as negative $250. These units are comprised of our 2 nuclear facilities, which is almost 5 gigawatts, because they can't turn off.
Right.
So they offer to the market at a price taking level because they have to clear power. It's also comprised of minimum load on some coal plants, also comprised of the ancillary service providing gas plants. There's a number of gas plants that are online to provide frequency management services. They're being paid for those frequency management services. In order to do that, they have to be online, which means they have to sell energy, and that energy gets bid in as price takers. So yeah, that's why, so we have about 15 gigs of price takers. And then on top of that, we have wind units that still have production tax credits that bid in at negative $25. On top of that, we have old wind units that are no longer eligible for PTC that bid in at $0 to $1, and solar facilities that bid in at $0 to $1.
Okay, so it's quite a mix. It's quite a mix.
Yep.
Yeah.
Yep.
Well, I wish we could carry on chatting for an hour or so, but we've really got to move on.
Thanks, Alan.
Thanks so much, Jack. Much appreciated. So yeah, our next speaker coming up now is John Plant. Now I have to say, John was obviously born for the job. He is the plant manager, Mr. Plant, at REG's Houston plant. So before I tie myself in total knots, I'll hand over to John to tell us about decarbonization through biofuel use and production. So John, over to you.
All right, thanks for that introduction there, Alan. And I would like to say that was the first time I've heard that, but yeah, it's pretty consistent with a last name like Plant and being a plant manager. A lot of people say, yep, I was born for the job. So I hope I serve it as well. So, but I appreciate the introduction and thanks for the opportunity to come today and talk to this group. I really appreciate it. As Alan said, I'm the plant manager for REG Houston. We run about a 35 million gallon a year biodiesel facility here in the Seabrook area on the east side of Houston. That plant's been there since about 2008. And what we do, we bring in some low free fatty acid materials, mainly beef tallow or soybean oil, in order to produce our biodiesel locally. So if you weren't aware of it, we're producing about 35 million gallons a year of biodiesel in the local area. So, and we're happy to do so. So the agenda we're going to go through is we're going to talk about who is REG, what do we do, what's our network, and then what products and processes do we use to make our biodiesel and renewable diesel. And then what environmental impact that has, and then we'll wrap up and see if we have any questions for the day. So a little bit about who we are. Lee, you want to go ahead and go to the next slide? I'd appreciate it. REG is a leader in the industry. We're an international producer of cleaner fuels and North America's largest producer of biodiesel. You can go ahead and proceed. So if you look here, you'll see that we have 45 terminals in the United States. And 12 biorefineries. You can see by this map here. Our home office is actually located in Ames, Iowa, and you can see kind of the concentration of terminals, biorefineries in that area, Mason City and Ralston. That's kind of where we got our start. And REG got a start as a farmer's co-op. And they realized that they could take soybean oil from the crush facilities and convert that into biodiesel. And so we created and started managing some plants and then started building our own plants and then running our own technology and producing biodiesel. You see that we service 45 states, 6 Canadian provinces, and 10 countries. So we have 10 biorefineries in the United States and then 2 over in Germany. You can go ahead and proceed, Lee, if you don't mind. So our products and processes that we use. So what we're making, we have 2 primary products, and that's biodiesel and renewable diesel. The biodiesel is a renewable fuel made from biological fats and oils, such as used cooking oils, distillers corn oil. We also use beef tallow, swine tallow, poultry fat. We've used some salmon oil, fish oils, things of that nature as well. And what we're really doing is we're taking using the transesterification reaction, as you see there at the bottom of this slide, And that's just a process of swapping one alcohol for another, in this case, methanol. We take that methanol and we react that with a triglyceride, which is any fat, and that ends up breaking that carbon chain and produces glycerol and methyl ester. And methyl ester in this point is that fatty acid methyl ester, or known as biodiesel. And so we run that through our reaction, and that's primarily what's going on in the biodiesel reaction. There's other steps in there, of course, but that's kind of the high level of the biodiesel reaction. If you proceed to the next slide. So what are some of the benefits of biodiesel? And we'll get into talking about that. It is an oxygenated fuel, which means you're going to have reduced tailpipe emissions, which is going to be less sulfur, less carbon monoxide, less hydrocarbons, less particulates. It's going to burn the fuel instead of losing it out of the tailpipe. So it's going to have a much less carbon impact because it's going to burn those particulates versus it going out of the tailpipe and causing carbon emissions. And we'll talk in a few minutes just about what impact that truly has to our environment. The other thing that's interesting about biodiesel, it provides a natural lubricity because it comes from a triglyceride. So it's going to run through your engine and actually help elongate engine life in vehicles that have diesel engines in them. So, which that is a nice benefit as well. It's comparable to vegetable oil in transport and handling. So there's not a placarded fuel. We're not having to run placarded fuels or as a hazardous product or anything. It's pretty similar to just running vegetable oil or transporting vegetable oil. So that's a nice attribute as well. It can be blended at any level. Most of the time, what we see is a 20%, especially in the state of Texas due to state incentives. Just to give you a little bit of information, most people don't realize that they may already be running biodiesel through their diesel vehicles. When you pull up to a fuel pump and it has a sticker on there, which is a requirement, you may see a little green sticker that says B2, B5, B10, B15, or even B20. And what that's doing, it's telling you the amount of biodiesel that has been blended with that petroleum diesel. So that's a real quick way to determine whether biodiesel has been blended into that petroleum diesel. And biodiesel right now is run as a blended fuel, and that's mainly due to the tax incentives that are available for doing those blends. Okay, thank you. In the renewable diesel realm, we have a facility in Geismar, Louisiana that currently makes renewable diesel. Renewable fuel, it's a renewable fuel composed of hydrocarbons that's made from biological oils and fats, still a triglyceride. So you start out with the same feedstock that's used for making biodiesel, but you're going to hydrotreat that instead. So we're going to use hydrogen and mix that with the triglyceride, which then gives you propane and paraffin. So it's a little bit different reaction. The front end's pretty similar, but the actual process changes up a little bit and you start using hydrogen and some higher pressures and temperatures to get that hydrotreating reaction. Okay, don't mind proceeding. So some of the benefits of renewable diesel, you of course have an exceptional cetane number. It's greater than 65, and that's considerably higher than the ULSD, which is around 40. And then that is a good indication for those of you that are familiar with cetane, how well it's going to burn through the engine. And then of course you get reduced tailpipe emissions as well. In particular, NOx and carbon monoxide is going to be less. Also, your particulate matter is going to be less. And something that people may not realize is now with the filters they're putting on diesel engines and having to regenerate those filters through there, you have to do that less by running renewable fuels through because it's not having as much go out. It's actually getting burned in the engine versus trying to pass through those filters. So you don't have to regenerate those as often. Also, it can be blended at any level. It's worth noting that straight RED is not the same as petroleum in spite of many marketing claims. There are some key aspects that are very different, such as additives, effectiveness of the elastomers, compatibility, density, and freeze point. Some users consider as a 50% maximum, but we are running some places where we're running 100% straight biodiesel. All right. So what are the environmental impacts of running biodiesel? It's kind of where the rubber meets the road, so to speak. Some of the places we see is in the transportation industry. This is the largest source of emissions. And so when we talk about the impact of biodiesel, we start talking about the impacts of vehicles on the road. And so we'll get into that a little bit more specifics about that in just a second. Also, customers are demanding more sustainable products. Biodiesel meets that need today. You know, you start talking about things of the future, well, you know, electric grid and the electric vehicles needing to have charge, but those still have to, you know, get powered. And so you see some reduction, but not quite the reduction that you need. Also, the electric vehicles, they're not quite capable of making those long hauls. So we still see the liquid fuel still being needed, because to haul heavy loads across the country, you still need that liquid fuel. So this way, through renewable fuels, renewable biodiesel and biodiesel, that allows you to do those long hauls and still have an immediate impact to carbon reduction. And then we're starting to see a lot of regulatory, well, not starting, we've been seeing it for a little while, regulatory pushes to lower carbon emissions. Municipalities taking the steps and saying, you know what, we need to lower our carbon footprint. And they start looking for ways that they can do that. And we can supply for that need today with supplying biodiesel and renewable diesel into those markets, into those industries, and into the municipalities. They can take those steps and lower their carbon emissions immediately by running biodiesel and renewable diesel through their fleet. If you can proceed. So this shows you some impact of what states currently have notable low carbon policies and tax incentives. You can see the state of Texas there does offer a tax incentive. That tax incentive for the state of Texas currently is 20 cents per gallon for B100 or B99, excuse me. And when I talk about B100, I kind of dropped a term there on you, B100 and B99. So biodiesel facilities produce B100. And to mix that, what we do to take that advantage of the tax incentive, we blend in a 0.1% amount of petroleum that allows us to take advantage of the tax incentive, which then becomes a B99.9. So you're blending down to 0.1%, which just gives you an opportunity to take advantage of that tax incentive. So you can see Texas offers that. So at the pump, what does that mean for our people that are supplying the fuel? It's about a 4 cents benefit when you're blending at a B20 ratio at the pump. So a nice little benefit there for people who can provide for cheaper fuel prices. Okay, if you want to proceed. So what are some of the, talking about low carbon solutions that are available now? We're taking a product that used to be thrown away and considered a waste, used cooking oil from, say, McDonald's or Taco Bell, any of those facilities that used to have to find outlets for their feedstock or for their waste oils, and they'd have to pay somebody to come pick that up, dispose of it. Some people were disposing of it improperly. Well, we've taken that, and now we've turned that into a commodity where a lot of these places now are having to put locks on their vats to keep people from stealing their grease because they found out there's a market for it. So we've taken something that was filling landfills and finding their way to places they probably shouldn't have been, and using that product, reclaiming it and making it into a fuel. The other benefit is there's a 5.5 times energy return ratio for making biofuels. So that's a nice payback for every piece of energy that goes in, having that 5.5% return in making that. Then a 50 to 90% lower carbon emissions when you run biodiesel or renewable diesel, either through large trucks or even passenger vehicles that have diesel engines. And we're looking at growing our distribution network to make it more readily available to the consumer and to people that are interested in running it. Okay, can proceed. So some of the comparisons I'd mentioned earlier about how biodiesel affects our environment and what's the impact. Well, REG's best-in-class biodiesel provides carbon reduction that we see in the comparisons here. Compared to ULSD, it's an 88% reduction of carbon emissions versus ULSD, 85% versus compressed natural gas, and 65%, even though we think of electric vehicles being so good, it still in reducing carbon, which they are beneficial, but at the same time, there's still having to be energy produced in order to charge those batteries. And what we can do is we have a 65% lower carbon emission even than electric vehicles. And in the California market, as Jack Farley had mentioned earlier, they're kind of ahead of the game in making strides towards carbon reduction. Even in the California market, running biodiesel is 42% an improvement over running electric vehicles on the California grid. So it's a nice reduction there, as you can see across the board by running biofuels. All right, you don't mind. So what's the impact of doing that? Well, in 2019, REG, from producing 495 million gallons of biofuels, we reduced about 4.2 million metric tons of carbon reduction. So that's a nice reduction in 1 year's time frame. And that's equivalent to taking 10.4 billion, and billion with a B there, miles by passenger vehicles. That's like taking those vehicles, parking them in the garage and saying, okay, we're not gonna allow you to drive 10.4 billion miles. That's the amount of carbon that was reduced by running that 495 million gallons of biofuels. And then also like replacing 4.6 billion pounds of coal being burned, 5.5 million acres of trees of replacement value of carbon, filtering that carbon. And then there, even with electric vehicles, 1.7 million passenger electric vehicles off the road. So that's what the impact can be. And that's in a single year related to those gallons. You can see that it can add up very quickly with the impact that running biofuels can have. Okay, you can proceed. So what does REG do beyond producing the biodiesel, which has such a large impact that you could see? Other things that we do at all of our facilities is we're looking for ways to even go beyond just the production of our biofuels, and that's installing automatic light switches in our plants to help lower that. So when someone's not in the room, it'll automatically shut off and not continue burning the electricity. We encourage recycling efforts at our plant as well, doing simple things like replacing disposable cups with washable ones, so those don't go into the trash and then have to be recycled. Also utilizing other forms of energy like wind turbines. We actually installed a wind turbine in our Albert Lea, Minnesota plant this year and looking for nice payback from that as well. So it's about that balance and trying to be good stewards of our resources. Of course, always we're looking at continuous improvement ideas to try to make good conscientious decisions and utilizing our resources. Thanks, Lee. So we come down to what can you do? Well, of course, first thing is you can run biodiesel. If you have a diesel truck or a diesel car, you can definitely find those green stickers at your filling stations and consider running that biodiesel. Not only is it going to lower the carbon emission, but it's also going to elongate engine life as you run that vehicle. So as it's lubricating and running it, and it's going to prevent you having to do as many regenerations of your filters as well. And then encouraging local elected officials and municipalities to consider lower carbon biodiesel and renewable diesel alternatives. There's bus lines, that are working with the city of Houston to consider running renewable fuels. A lot of places, if you go to Texas A&M, you'll see on the back of their bus lines that run around the campus, they're running some renewable fuels in there as well, biodiesel. So that's nice to see. But getting the word out and letting people know, people talk about, well, we need to lower our carbon footprint. Well, this is an immediate way to do that. And it's not something in the future that we have to wait for or have to figure out. It's available now and can be run in vehicles without or very little financial investment, because it can run in regular engines just as they are. And then promoting the education and understanding of renewable fuels. Just letting people know you attending this discussion is a step towards that, just so you have a little bit better understanding of it. And when you get into a conversation about it, you're a little bit better equipped to have those discussions and inform people about it, because a lot of people just don't understand it, aren't even aware of it. Very few people know that we have a 35 million gallon a year plant here in our local area. And so it's just getting that education out there and helping people understand that it is readily available to them. And then looking for opportunities to limit your power use at the house, turning the lights off when you're not in the room, things of that nature to try to help, and then recycle and reuse where it's possible. Just trying to be good stewards of our resources and trying to balance those things. And biodiesel should be definitely part of that. Okay, Lee. that kind of wraps it up for me. If there's any questions, Alan, hopefully I've helped you catch up on some time there.
No, we're in good shape, John. So yeah, we have time for several questions, and have seen several come in. So let me just find that page again. Question there. Perhaps you can explain this. This is sort of fundamental. How is using soybean oil as biofuel giving a reduction in carbon emissions? Would you like to go into a little bit of how that works?
Yep. So a couple of things. Soybean oil, as we use that to produce, so soybean oil, we'll go that and use that as our triglyceride. Running that through our process, that soybean oil will then be converted into biodiesel, and then that gets ran into the vehicles. And so it's going to produce less carbon out of the tailpipe by replacing that ULSD. When it's ran as a blended fuel, we're replacing, say, in a B20, that's 20% that you're running through a vehicle that's going to reduce that carbon emissions. And we're taking soybean oil from the crush facilities after all the nutrient value comes out of it. When we talk about utilizing renewable fuels, we say food before fuel. So we're not taking food away. We're not taking the edible parts of the soybean away. We're taking what's left over after that has been extracted. So we're taking a product that used to be a waste, and now we're taking that and turning that into a fuel. So there's benefits from that, from not having to take it to a landfill or treat it as a waste product. You're actually converting that and taking that to as a fuel value. So there's several levels of carbon reduction in there, from eliminating the waste, as well as now you're producing a fuel that's producing less carbon out of the tailpipe when it's blended with ULSD.
Okay. Let's see other questions here. Is there investment? Is the investment in renewables subsidized by any government entities at the moment? So
it is. There's called the Renewable Fuel Standard, and that's actually active through 2022 currently. To where there's a $1 per gallon tax incentive for produced gallons, and that's part of the renewable fuel standard. And then there's also in the California market, there's a carbon intensity tax that it also has a benefit, which makes California a very attractive market to send biofuels to.
Okay, great. And just going back to your earlier discussion about the use of the soybean oils, question here was how much of your feedstock truly is waste products versus oils diverted from food production. So in your case, it's all true wastes, is it?
It is, yeah. We don't use, so once it comes through the crush facility, we'll take a side stream from the waste of that crush. The fuel and the food and everything that can be utilized is pulled through the crush facility, and then we take the stream of waste out of those facilities. So the stream that used to would have gone to a waste product that would have to be hauled off now goes to, in several cases, directly to our plant, and we're using that. And so it's 100% would have been waste, and now we're recycling that.
Right. Guess just one other question here, and then I think we're going to have to stop. But what is the cost of biodiesel versus petroleum diesel?
Yeah, that's usually a pretty common question. It's actually very comparable to ULSD, depending on the market that you're in. And when we looked at that map in the presentation of the different incentives in the different states, will be dependent on what the cost comparison is compared to ULSD. But it's very comparable. A lot of times it's actually cheaper. Excuse me, in the Texas market, we talked about that 4 cents benefit. So it can actually be cheaper in a lot of states, in a lot of markets. So where it's not, it's comparable in all of them, but some it's considerably cheaper. So if you're getting 4 cents a gallon reduction in price, that's a nice benefit. So comparable at the worst, and a nice benefit at the best.
Great. And I guess we do have a little bit of time in hand. So what are the trends in production at this point as far as?
Yep. So some of the trends in production, what we're seeing through the industry is renewable diesel is really starting to, we're seeing a lot of people jump into the game for that because there is a nice margin in that realm right now with renewable diesel. So there's a lot of the companies are starting to jump in and try to take advantage of that opportunity of those larger profit margins, especially with renewable fuels going to the California market. So you're starting to see larger industries. REG is the nation's largest producer right now, but you're starting to see some of the other larger petrochemical industry players coming into the game, Phillips 66, ExxonMobil, places like that are really looking at opportunities to get into the renewable fuels game to try to balance that and help lower their carbon footprint by producing those gallons. So it's renewable fuels, renewable biodiesel is kind of the growth where we see now. Then there's opportunities. We didn't get into much discussion about the blending of renewable diesel and biodiesel, which REG calls REG Ultra Clean, which is a blended fuel of renewable diesel and biodiesel. And then you get benefits and advantages from both of those fuels. You get the lubricity benefit from the biodiesel, and you get the low cloud point related to the renewable diesel. So it's a nice blended fuel that can be used. But that's biodiesel is kind of running, still growing. There's still people interested in doing that, but renewable fuels is getting a lot of it. Renewable biodiesel is really getting a lot of attention right now.
I guess one question alongside that, your supply chain for the feedstock, how does that work out? Because presumably there are limited amounts of used, for example, used cooking oil available. So how does the supply chain work? Is that a major problem to you?
So it can be a challenge depending on what's going on right now. The pandemic and COVID acting like it is, it actually has caused people to go to less restaurants, less out, eating out, and so we see less in the used cooking oil markets right now because of that. It depends too on our weather. If the crops are good and we have a large soybean production, then we'll see larger amounts of feedstock in the industry and in the market. We buy that on the open market. It's traded, and so it depends on what's going on. And so we'll see impacts. It's surprising, things that impact us on feedstock. But if you have issues like we saw the issue with the poultry farms getting issues going on there, and then the following issue a couple of years later with the swine farms having that swine flu go through there. Sure. And I was, I had impact being from Houston, Texas, and growing up in Texas. I would talk to some of our traders one day, and I said, when we have our livestock shows going on, the Houston Livestock Show and the State Fair and the San Antonio Livestock Show, I said, how do you see that impact in the market from all those animals flooding into the market in February, March? And he said, well, John, we usually see, 25 to 30,000 animals probably come from those livestock shows, but you got to understand they're processing 5 million pigs a day. So it's just a blip. It's not even, doesn't even create a blip, So as far as the squeeze on the feedstock, it just depends on how it's going. Is a good crop season? Is it a good season for, for processors through the meats, as the beef and the swine? Are they having good years? It all is relative and ties together. So we'll see that fluctuation of feedstock depending on what's going on in the environment around us.
Well, great. Thank you so much, John. And I think we are going to have to stop there. Time has sort of caught up with us. I'd like to say thank you very much to all of our speakers. It's been a very interesting set of presentations here, and we greatly appreciate it. Apologies to those of you that I wasn't able to get to 100% of the questions, but I think we got most of them in. So at this point, just wanted to remind you about a couple of things. So we have the PDH certificates. The site should now be open for those. So you should be able to collect your certificates if you want to get it. And the link is now back in the chat. So if you want to follow the link, and you'll be able to claim your certificates. So thank you all for joining our webinar. Yeah, very good. That's better. We do hope that you'll be able to come to some of our future events as well. And just to give you a bit of a heads up on those events, we do have our teen webinar. And for those of you who are thinking this is a youth program, no, it's not. TEEN is the Texas Industrial Energy Efficiency Network, which is a number of publicly funded organizations that are at work in the industrial energy efficiency space. And so the TEEN webinar is about turning energy efficiency into cash savings. And that is next month, April 15th, 2 till 3:30 p.m. And then in 2 months' time, on May 6th, which is another Thursday, we'll have our water forum about reducing water use in manufacturing plants. And again, as before, you'll find a lot more information on these events on our website. And with that, oops, if I can get to the next slide, okay. The STS meeting, the monthly meeting, will be starting in roughly 5 minutes at 6 o'clock. And at this point, we'll give you a short break until that starts. We'll stay on the same link for the STS meeting. So thank you again, everyone, for joining. Thanks again to our speakers, and much appreciate all your time. Thanks a lot.
Alan, thanks for the opportunity, sir.
Well,
Appreciate
thank
it.
you, Sam. Great.
Yep.
It's been good.
Have a good evening.
You too.